So he got a grant from the Wellcome Trust. This is a really good gig, and these grants are actually available. So if any of you become serious scientists, you can apply to the Wellcome Trust, and they'll give you money to cross the Atlantic 3 times each, to sit in a room and talk about what the art you do and the science you do together, and you don't have to produce a paper, you don't have to do a project, no reports, no publications. You just have to record everything you say to each other so other people can study how an artist and a scientist talk to each other. And which is good. So I got to go to London for three visits, and Jane came to New York for 3 visits. And when I mentioned this trivial versus robust thing, she said to me, and because we recorded everything, I know it was in my office on the 9th of May, 2002, ideas about pathways are interesting. A lot of people who are involved in digital biology who knew there was something like that. Although when I said that to her, she said, well, Pac-Man, which I know you're very young and you think that's ancient history, but okay. She's as old as I am. Are interested in things like swarming people and so-called soup organism behavior. And one of the useful models to take forward is about ant colonies. And this is where she started to introduce me to complexity theory. And ants in particular, which I'm now going to spend a lot of time talking about, are a really useful way to explain complexity theory. And this is where my career sort of went off on a completely different tangent yet again. So complex adaptive systems, what do we mean by these? If anything I say here sparks some interest, these 2 books are really terrific explanations of complexity in detail, but for lay people, and they're really good reads. Even my mother read one of these. And you'll see why. One is called Complexity, Life at the Edge of Chaos, and the other is called Emergence. We'll get to what that means shortly, too. So complex adaptive systems are defined as groups of interacting individuals that, if they fulfill 4 simple criteria, they organize themselves from the bottom up into larger scale structures that appear planned from the top downward, but are not. And these structures that they self-organize into are referred to as emergence or emergent self-organization. So this is all about how interacting things organize in a bottom-up fashion instead of getting themselves organized in a top-down fashion. How do we know that if they appear top-down, how do we know that they're not? Well, it turns out that any kind of complex system you can think of, and ant colonies are a good example, if you computer model virtual ants to make a virtual colony, and if you get the details of how ants interact with each other through pheromone signaling and through how they respond to changes in their local environments, if you do that and set it running, the ants in your virtual ant colony will actually create a virtual ant colony that's identical to an ant colony in the wild, even though you don't program the food lines, the cemeteries, the queen, the tunnel building, etc. I don't need to show you this, I just said this. So we know that without planning things from the top downward, just setting the ground rules from bottom, lowest level interactions, the whole thing will self-organize on its own, if you get it right. And this is why computer modeling is important in things like, for example, economics. Complexity theory is now the dominant model for how people study how economic markets rise and fall. Urban development, if you're familiar with the work of Jane Jacobs, she was talking about cities self-organizing way before complexity theory existed as a field, but she had already intuited that this is how cities develop. My favorite example is Beatlemania. You know, if you think the Beatles are the greatest rock band who ever lived, well then of course Beatlemania was a reasonable response. But if you listen to the Beatles talking about their experience on the Beatles anthology tapes, they're very clear that it wasn't them, it was the Screaming Girls. And that every creative innovation they made was in response to the way their fans were changing their responses. And as that became this thing they had to wrestle with, they kept responding. So Beatlemania is a bottom-up thing. They were creative enough to figure out how to respond. So there's an element of top-down, there often is, but the essentials are bottom-up. One of the few things that, where this has been applied routinely in biology is in immunology, and also consciousness studies. This is one of the dominant models how consciousness might form as self-organization of neuronal networks, which themselves are self-organization of neurons, which themselves are self-organization of all the cells in the brain, blah, blah, blah. So what are those 4 criteria that I mentioned? Number 1, numbers matter. If you have 3 ants, you don't get an ant colony. But if you have 25 ants, it's sufficient. If you have 100 ants, you'll get a more sophisticated, more complex colony. 1,000 ants, still more complicated. 1,000,000 ants, still more complicated. So you have to have a certain number. One of the areas of research is what defines what that threshold would be. And the more you have, the more complexity you get. There has to be a predominance of negative feedback loops in the system. If you have a predominance of positive feedback loops, you can have positive feedback loops. But if they predominate, you're not going to get self-organization. Or if you do, instead of being adaptive, responding to a changing environment, it'll be self-limited and energy expending. So think tornadoes, hurricanes, I would argue cancer. This is a good way to explain cancer, which we'll come back to. Interactions between the individuals are local. They're only paying attention to what they're doing and what they can perceive around them. There's no ant in the colony figuring out, is there too much food? Is there too little food? Do we need more ants? Do we need fewer workers, etc.? They're just paying attention to what's going on locally. And the neatest thing, and this is what Jane was bringing my attention to, is that there has to be low-level randomness in the system. If there's too much randomness, then you get complete disorder. Or if it's the right kind of randomness, you can get fractal chaos if you're describing a system mathematically. But if you don't have any randomness, then the system can't change if the environment it's adapted to changes, because there's no way to explore new possibilities. And so you need this intermediate value of randomness, just enough but not too much, but not too little. So, and this is often referred to as quench disorder, which will bring us back to something else your teachers have lied to you about shortly. They don't know that they're lying, just the word hasn't gotten out yet. So if you look at a food line of ants, it looks like a straight line. But if you look really carefully, there's always 2 to 5% of the ants that aren't following the line. This is the quench disorder in the system. And if the food runs out, it's the ants that aren't following the food line that are likely to quickly find other food sources and establish a new line. Think about it. If every ant in the colony was on that line, what would happen when the food ran out? They'd still be running along that line. There'd be no new food. So you need this disorder in the system, this quench disorder in the system, to explore new possibilities. It turns out if you put your foot down in the middle of the line, it's these divergent ants that very quickly will establish the shortest and quickest route around your foot. And it was noted, oh God. There are a handful of people in the room who were using landline telephones in 1972. Do you want to raise your hands and embarrass yourself? It used to be, you know how your cell phone sometimes just blits out? Landlines used to do that, believe it or not. And even with a local phone call, you'd be talking on the phone and you'd lose your connection and you'd have to call them back. Well, Bell Labs was studying ant colonies, and they were one of the early centers for the study of complexity research. And they started to code into the phone lines divergent ants. And in 1972, they figured if you put in random elements into the phone line coordination system, then you still lost the connection, but the new connection would be established so quickly that the people on the phone wouldn't even notice that it happened. And that's why we don't lose connections on phone lines, because there are random ants in the computer modeling for phone connectivity. Why they can't do that for cell phones, I don't know. So what Jane was pointing out is that while from a distance an ant line looks like a straight line, up close you see that there's randomness in the system. And she was suggesting that while cell lineages look like this unidirectional hierarchical thing, now we're looking more closely with more sophisticated techniques, and we're finding low-level randomness in the system. So this suggested that cells might themselves be members of a complex system that give rise in a self-organizing fashion to tissues, organs, bodies, embryologic to fetal development to postnatal development. And are there enough? Well, we've got 4 trillion human cells in our bodies, so yes. They mostly interact by negative feedback loops. And as I said, I would argue that cancer is when you have too many positive feedback loops, it becomes non-adaptive, energy expending, and self-limiting. No cell is paying attention to whether you're hungry, sleepy, horny, cold, whatever. They're just paying attention to what they're doing in their local environments. And now we're showing that there's quench disorder in the system. And it turns out there are many kinds of quench disorder in the system, but this was the first time, I think, that anyone published in this way. And so what we said in a series of papers is that low-level engraftment of cells from the bone marrow into various organs is not only not trivial, but it is vital, literally so. It's this randomness in the system that makes your cells into a living entity that has tissues that grow and develop and maintain and can adapt to a changing environment. This is what makes you alive. So if we say that, if we define cells as members of a complex system, this has implications according to complexity theory. One of my favorites, being a child of Holocaust survivors, is mass extinction events. We're always looking for the moment things are going to collapse, you know. So if you mathematically, there's no one in the room who thinks that's funny, okay. If you grew up in my neighborhood. So you can draw order and disorder as a phase diagram, and it looks something like this with fractal chaos in this zone, perfect order like predictable billiard balls, complete disorder like molecules in a gas, and then, as I said, fractal chaos. Mathematically, complexity lies at this edge here. And that's why Richard Lewin called his book Complexity: Life at the Edge of Chaos, because this is where complex adaptive systems arise mathematically. So you should be able to plot any complex system at a specific point. But because there's quench disorder in the system, you can't do that. They tend to wander around in this zone. And given sufficient time, it may, in the case of a hydrogen atom, be the entire lifetime of the universe, but given enough time, eventually it will wander outside of that zone into chaos, and you'll have a mass extinction event. It's inherent in the mathematics. It's unavoidable. So if we think that cells represent complex systems, they are subject to mass extinction events. So you can look at some diseases like aplastic anemia. There are lots of theories what causes aplastic anemia, where the bone marrow just completely crumps out for no apparent reason. But maybe it's not a virus or a gene or an environmental toxin. Maybe it's just that with 10,000 people, 1 in 10,000 is going to have aplastic anemia, just mathematically, probability speaking. 100 people get hepatitis A, 1 of them is going to die or get a transplant. Is it something special about that person or their virus, or is it simply inherent in the mathematics of disease spread where hepatitis A is concerned? No one's ever done the kind of population studies necessary to answer this, but it's an answerable question. It also means that the price of being alive, being a body made of cells that can adapt, necessarily you're going to die. They're like two sides of the same coin. There's no such thing as a fountain of youth. There's no such thing as eternal life for this body. It necessarily will collapse given enough time. Which is, should actually, when I give this talk for physicians who are out in the world, they usually smile and sigh at that point, but you're looking at me with eyes filled with terror. So, but know that this will be comforting one point, because you're not going to save everybody, let alone yourselves. It also implies that hierarchies of complex systems can exist, and this is where it gets a little bit extra interesting. We've already sort of hinted at this. From a distance, an ant colony looks like a thing, but if you go up close, it doesn't look like a thing at all. It looks like phenomena arising from smaller things. But the bodies of the ants themselves are made of cells, and so we know if we go to the microscopic level, in fact, the body of the ant disappears, your bodies disappear, into a collection of cells that are interacting with each other. And so whether something appears to be a thing that's solid and real, or a phenomenon arising from smaller things, depends on the scale of observation. Now, my boyfriend and I were in Rome last November. It was his 50th birthday, and friends of ours had an apartment for us to use in Rome, and so I took him to Rome for our 50th. And the friends there we haven't seen in 6 years. And we're walking, the first night we arrived, we're walking along the Tiber, we're crossing a bridge, and one of the friends says to me, "So what are you studying research-wise?" And I'm trying to explain this to him as we're walking down the street.